Well, we would like to share our experiences about remote access in our facility. So we will split a bit our presentation. So our main focus today is to show how we improve the measurements of solid state NMR measurements via curing and managing remotely. So for this, we would like to introduce our facility. Our Magnetic Resonance Research Center is at Radboud University in Nijmegen. We have spectrometers for both solid and liquid state. And also we have access to the 1.2 gigahertz spectrometer in Utrecht, as was mentioned previously, and also a shameless advertisement, as I heard before. Our facility is also part of Panacea. So here we listed how big is our group. Mainly the academic staff and the students and postdocs have access to remote access for the spectrometers. And on the pic on the right, before the pic of Arno, that is our supervisor, our spectrometers are located in a separate building, that is the Haugens building. So it's like 5 minutes walk, but sometimes, you know, as somebody else mentioned, you don't want to go downstairs and perform the measurements. So mainly we provide access for remote via any desk. For us, work very well. So Job will show us later how he does this. So in this case, we would like to mention how we improve the efficiency of solid state measurements by an external automatic machine and tuning robot. And the main application of this is especially for when performing white line NMR experiments. And also another big advantage of this is that we can improve the time of the measurements in outside working hours, which can also facilitate the measurements for our users. When recording white light NMR measurements is mainly acquired by a box type of acquisition. And the main application of this can be, for example, for a static or spinning experiments, also for recording some quadrupolar nuclei and other nuclei that are really or have really wide line spectra, and this, when we are talking about several megahertz, that is beyond the bandwidth of the probes. So this is the main application. Also are some examples in one of the publications that will be listed maybe in the next slide. You can get more information on about this robot, and also some applications for batteries, etc. In our case, Job will show us how he used this external robot to record NQR experiments. He will explain us a bit more about it. And other of our PhD students are using this robot to record NMR measurements, static NMR measurements on batteries. So I will give the word to Job.
Yes, so hi everyone, I hope my microphone is okay as well. Here you can see one of the spectra that I took during my internship, which is all about NQR. And as NQR is always white line NMR, I started using the ATM as a way to make it more efficient. But incidentally, this is also a way to do this kind of experiment remotely, where otherwise you would have to have a very dedicated local operator. So I figured I'd tell you about how this works. So this is the robot in question. So here you see the bottom of my probe is in the top of the picture. So the ATM is a box with 2 rods which you attach to an existing probe. So the probe itself has not been made specifically for this kind of automatic tuning and matching. You can just buy this kind of thing. So I have a reference to the paper here. It's built by a relatively small German company called NMR Service. And if you have this kind of thing, then all your existing probes, or at least all your normal existing probes, which have been made for human matching and tuning, become available for doing this automatically. because it simply rotates the tuning and the matching sticks as you would do with your hands, except it now does it with a motor. So schematically, the setup then looks like this. Here in the bottom, you see you have this ATM, which is connected to a console which controls it. And the console itself is attached to a regular PC. And of course, the PC can be internet accessible. And this is where the remote aspect comes in. So as Jennifer told you, we simply use AnyDesk, which works fine. And then you get a little program through which you can, from your desk, you can just tune the rods however you want. So you get two modes of operation once you have this set up. The simple one is, it's called manual mode. You're not, it's a bit weirdly named because you're not using your hands, but still. So the only real difference when you're tuning and matching yourself or using this robot in manual mode is that you press buttons instead of using your fingers. So it requires very little setup. Really, you only need to connect all the right parts, and you need to calibrate the ATM. So the ATM needs to know where the hard limits of your tuning and matching capacitors are, because if the user accidentally goes past it and the ATM doesn't know that there's a limit there, then it will just continue and it will damage your capacitor. But that's really the only thing that you need to do. So everything needs to be connected, you need to calibrate it, and then the local operator can just walk away. And the remote user can use the buttons here to tune and match as you normally would using your normal spectrometer software to check whether your tuning is okay. That's the easy method, but it's not really, it doesn't save you any kind of labor. It only really saves you from having needing a local operator. If you want to save the labor as well, and for example, tune and match during the night, then you might want to use the automatic mode, which is really what it's advertised for. And in that case, the ATM will measure how good the tuning and the matching is, and it will employ a search algorithm to tune the rods itself until it's satisfied. This is very useful, but there's a couple of additional problems here. It's more involved mostly, so you need to edit the pulse sequence because suddenly your PC needs to communicate with the ATM instead of only having a direct connection to the motors. You also need to fine-tune the algorithm a bit. There's various parameters, as you can see here in the bottom. This is just a snapshot, and they all depend a bit on your experiment. So if tuning is relatively easy or very fine, then you might want to tune to turn the rods slowly or faster, etc. The main problem with this mode, especially compared to the other one, is that it's currently not perfect in our experience. So it glitches. Mainly this means that it will occasionally forget the calibration that you did, which is obviously dangerous. This has two consequences. The first one is that suddenly your local operator is no longer free to do other things because he needs to be on hand to recalibrate your setup if something goes wrong. The other one is that the remote user needs to have some level of expertise of the ATM to spot the problem before it damages anything. It doesn't happen a lot, but obviously you don't want to have this kind of risk, normally speaking. So that's something to keep in mind. Still, if it works, it's very nice because you can just give it a list of frequencies to tune to, or you can give it the same frequency 100 times if you wanted to tune back in case it detunes, and then you can just press the button and you can walk away, which enables you to do all this kind of thing from your office instead of having to be there physically. And I figured I'd give you a little demonstration of how this works. It should be pretty fast. So let me share another window. Yes. Okay, so this is just AnyDesk. And you can see here, wait, what have I AnyDesked into? Is this correct? No. No, this is session playback. Let's not do that. That's silly. No, we want this one. There we go. Okay. So I just connect to my spectrometer computer. This is R-NMR for the people who are more experienced with topspin. It's just a sort of variant equivalent. And I've got another AnyDesk open to the laptop which has my ATM software on it. So I put it a little bit to the side so that I can see it both at the same time. And first, of course, I want to check the tuning. So I go to this is the frequency that the resonance should be. And you can see that's a little off. Now, I could tune it by hand so that it's correct. But I'm not going to do that because I want to show you the automatic tuning. So instead I will detune it further. So I simply enable the manual tuning and I tune down and I match down. And after a bit of backlash, you can see that my tuning curve is moving away. So this should be enough for the demonstration. So this is very simple, and I could do this, if I was willing to spend the time, then this would be sufficient and very safe. But if I don't want to spend the time, then I activate the automatic tuning. The controller needs to be reset. And then I activate the pulse sequence through a Python script. That is mostly because I have some safeguards built in so that the automatic tuning cannot go too wrong. But it's not essential to the operation. So let's see. You see that the program is waiting for my signal. So I say, okay, do this experiment, override, yes, please. And then I go back to here to see what's happening. It's a bit small, but you see here that this number, the standing wave ratio, is an expression of how good the tuning and the matching is, and it's now not very good. So it's tuning up this number. And now it has already found it. So this is a good number. It's green. It switches to pulse sequence. I do an acquisition. That takes 13 seconds. And we can just wait a while because I put in two frequencies that I want to measure, and it will do both in sequence without me having to do anything. So that's one. Now you will see I measured at 164 megahertz. Now I measured 250 kilohertz above that. And now the SGLBR is wrong again. And it's going to look for the right number. So first it's tuning in the wrong direction. The number is getting worse, but it will execute its search algorithm and we can just wait. And eventually it will find a good number and then it will measure the second time. Let's go down. There we go. And now it does a second acquisition at this new frequency. Right. We can wait for this, but really the point has been made. Let me now switch back to my presentation. That's this one. Yeah, so what can you do with this kind of thing? Well, I think in solution state, this is really all quite not as relevant because as I understand it, solution state NMR already has automatic tuning and matching. But in solid state, I think this opens up quite some possibilities of experiments remotely that would otherwise be almost impossible. So I've showed you NQR, but that's really goes for any kind of white line NMR. You can also do it for any kind of normal quadrupole NMR where the quadrupole effect is very strong. All kinds of other things where you need to change the frequency or not even change the frequency. If you just have a very long experiment, which for some reason the tuning changes during, for example, you're doing an in situ experiment, then you can use this kind of ATM to correct for that without having without needing a local operator or being awake at night. So I think that kind of shows the things that I wanted to tell you. So in summary, if you have this kind of ATM, it's a very flexible addition to your existing equipment. You only really need to buy the one machine and you add it to your existing probes. And as long as the probes were meant for human hands, then it should work with a little bit of technical support perhaps, but mostly it should work. And then you have access to tuning and matching over the internet. And you can do that in 2 separate ways. You can do it manually, which is very safe, and you can do it automatically, which is very promising, but there are some imperfections which you need to be aware of, especially when you're allowing remote users to potentially damage your capacitors. And that's it. So if there's any questions, then I'd like to hear it.